Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Inside every gearbox, bearing, crusher, conveyor drive, and compressor, one invisible force continuously damages machines: friction. Today, engineers are exploring graphene-infused lubricants to reduce friction, control wear, and improve machine reliability. In heavy industry, friction is not a small issue. It creates heat, damages surfaces, increases vibration, wastes power, and finally causes breakdown. A global Tribology study estimated that about 23% of total world energy consumption is related to friction and wear. A polished shaft or gear tooth may look smooth, but under a microscope it is full of peaks and valleys. These microscopic peaks are called asperities. When two surfaces move, asperities touch, break, weld, and tear apart. This is the starting point of wear. Lubricant protects machinery by forming a thin film between surfaces. This oil film reduces metal-to-metal contact, carries heat away, removes wear particles, prevents rust, and improves equipment life. Machines do not always operate in full oil film condition. During startup, overload, low speed, or shock load, the oil film becomes very thin. This is called boundary or mixed lubrication. Graphene additives are most useful in these difficult zones. Graphene comes from graphite, the same material used in pencils. In 2004, Andrei Geim and Konstantin Novoselov isolated graphene using adhesive tape. Their graphene work received the 2010 Nobel Prize in Physics. Graphene is a single layer of carbon atoms arranged in a hexagonal honeycomb structure. It is extremely thin, strong, thermally conductive, and has very high surface area. Graphene-infused lubricant is normal lubricating oil or grease enhanced with graphene-based nano-additives. These may include graphene nanoplatelets, graphene oxide, or reduced graphene oxide. Graphene must remain properly dispersed in the oil. If it settles, clumps, or blocks filters, it may create problems. So the real engineering challenge is not only adding graphene, it is keeping it stable and compatible. When graphene reaches the contact zone, it can form a protective tribofilm on the metal surface. This film reduces direct metal-to-metal contact and helps protect the surface from wear. Graphene has a layered structure. These thin carbon sheets can slide over each other more easily than rough metal surfaces. This reduces resistance to motion and lowers friction. Graphene particles can enter microscopic scratches and valleys. This may reduce rough peak pressure and make the surface smoother. In one 4-ball test, 0.035 Wt% graphene lubricant reduced friction coefficient by 40.8% and wear scar diameter by 50.4% compared with pure oil under tested conditions. In boundary lubrication, the oil film is very thin. Graphene can help carry load at the micro-contact zone and reduce direct asperity contact. Friction generates heat. Graphene has high thermal conductivity, so researchers study it for improving heat transfer in lubricated contacts. To test lubricants, engineers use machines like the 4-ball tester. It measures friction and wear scar size under controlled load, speed, temperature, and time. After testing, the wear scar is measured under a microscope. A smaller wear scar means better anti-wear performance. This helps engineers compare normal oil and graphene-enhanced oil. Graphene must be added in the correct amount. Too little may not help. Too much may cause agglomeration, filter problems, or higher friction. The best performance comes at optimum concentration. Industrial gearboxes are strong candidates for graphene lubricants. Gear teeth experience rolling and sliding contact. Under heavy load, graphene may reduce scuffing, pitting, heat, and wear. At the contact point of gear teeth, pressure is extremely high. If oil film becomes weak, wear begins. Graphene may help by forming a protective layer in this contact zone. Bearings fail due to fatigue, poor lubrication, contamination, and overheating. Graphene-based lubricants may help during start-stop operation, low speed, and high load conditions. In precision bearings and high-speed systems, particle size is critical. If graphene particles are too large or unstable, they can disturb the oil film. So OEM approval and testing are important. Hydraulic oil must transmit power and lubricate components. Graphene may reduce pump and valve wear, but hydraulic systems use fine filters, so filter compatibility is essential. Graphene can also be used in grease. It may be useful for bushings, open gears, pins, slow-speed bearings, crane wheels, and mining equipment. Graphene lubricants may be most useful in heavy-duty gearboxes, mining crushers, cement mill drives, steel rolling mills, conveyor systems, open gears, bushings, and slow-speed heavily loaded bearings. Graphene lubricants are promising, but they are not magic. The major challenges are dispersion stability, cost, quality control, filter compatibility, and long-term field testing. Before using graphene lubricant, engineers must check OEM approval, seal compatibility, filter compatibility, viscosity, oil analysis trend, vibration trend, temperature trend, and wear metal results. The correct method is controlled field trial. First, collect baseline data from existing oil. Then use graphene lubricant in one selected machine. Monitor temperature, vibration, oil condition, filter pressure, and wear metals. Graphene-infused lubricants work through multiple mechanisms: protective film formation, low shear sliding, microsurface filling, load support, and possible heat transfer improvement. The future of industrial lubrication may not depend only on thicker oil. It may depend on smarter oil engineered at the nanoscale. Graphene is only 1 atom thick, but in the world of heavy machinery, it may become a powerful shield against friction and wear. If you want more engineering documentaries on industrial technology, machinery science, and future manufacturing, subscribe to SimpleGAN.